You know, we're surrounded by all these invisible forces, right? But one of them is basically the secret engine of our entire modern world. Today, we're going to pull back the curtain on this hidden connection between electricity and magnetism. And it all starts with something surprisingly simple, a moving charge. So, think about this for a second. What in the world could possibly connect a giant industrial crane, a life-saving MRI machine, and, say, a super quiet electric car? I mean, they seem like they're from completely different planets, but they all share the exact same secret. And the answer is, well, it's almost ridiculously simple. It's just moving electricity. Yep, a basic electric current just flowing through a wire. That's the key that unlocks all of these amazing technologies. But that's the big question, right? How does a simple stream of electrons create something strong enough to lift a car? See, it's not just that electricity causes magnetism. The real mind-blowing discovery was that these two forces, they aren't separate things at all. They're two sides of the same coin. They're fundamentally linked, part of one single unified force that honestly runs almost everything. And we call this unified force electromagnetism. The core idea is super simple to grasp. Anytime you have an electric current, anytime charges are moving, a magnetic field just appears. It pops into existence, wrapping itself around that current like an invisible whirlpool of energy. All right, so let's dig into the first piece of this puzzle. How does a simple little current create this powerful magnetic field? Okay, you're going to see this name, the Biot-Savart law. Don't let it scare you off. Seriously, just think of it like the user manual for magnetism. It gives us all the rules, telling us everything we need to know about the magnetic field that a current creates, how strong it is, which way it's pointing, and even what shape it takes. And the best part is, the rules are actually really intuitive. It makes perfect sense. You want a stronger magnetic field? Well, you can either crank up the current flowing through the wire, or you can just get closer to it. That's it. It's a super direct, predictable relationship. So, once you know the rules, that's when you can start having some fun. Let's take a look at how we can actually bend these fields to our will and make them do what we want. And this is a perfect example of a key idea here. The shape of the wire is everything. Look at the image on the left. You've got a straight wire, and the current creates these big, circular magnetic fields around it. But check out what happens when you bend that same wire into a loop, like on the right. All of a sudden, you focused all that magnetic power right smack in the middle. You know what's really cool, though? We have this super easy way to figure out the direction of the field. It's called the right-hand rule. Seriously, you can do it right now. Just point your thumb in the direction the current is flowing and look at how your fingers curl. That's it. That's the direction of the magnetic field. It's not just a neat trick. It's a fundamental law of the universe, right there in your hand. Okay, so let's build on that. If one loop is good at focusing the field, what happens if we take a wire and wrap it into hundreds of loops, all packed tightly together? Well, that gives us something called a solenoid. And the real magic of a solenoid is that inside that coil, you get this incredibly strong, perfectly uniform magnetic field. It's like creating a magnetic tunnel. All right, so we figured out how to create magnetic fields. Awesome. But that's really only half the story. The real power, the game changer, comes from what happens when those fields start interacting with other things. Yeah, a magnetic field isn't just sitting there. It's an active force. Its whole job is to push and pull on any other moving charges that happen to pass through it. It's constantly looking for something to interact with. But there's a catch. A big one. The direction the charge is moving is absolutely critical. So if a particle is moving perfectly parallel to the magnetic field lines, nothing happens. It's like the particle is completely invisible to the field. It just keeps on going in a straight line, totally unaffected. But look what happens if that same particle tries to move across the field lines. Bam! The magnetic force grabs it. It acts like an invisible rope that just yanks the particle sideways and traps it in a perfect circle. There's no escaping it. And that right there, that ability to grab and redirect moving charges, that's the whole secret. That is the fundamental principle that lets us turn electrical energy into actual physical motion. So let's bring this all back to the real world. Where do you actually see this principle of turning electricity into force in your everyday life? You'd be surprised. Well, on a really small, sensitive scale, you find it in devices like a galvanometer. Here, even the tiniest little electric current creates just enough of a magnetic field to twist a coil and move a needle. It's literally measuring that tiny electromagnetic push. Now, let's scale that way, way up. Instead of just twisting a tiny needle, we use that exact same force to spin a heavy rotor with incredible power. That's what creates the torque to drive, well, pretty much everything, from your desk fan to a Tesla. And once you start looking, you see this principle is literally everywhere. It's in those giant electromagnets in junkyards lifting cars. It's what makes your car's ignition system work. It's how speakers and microphones function. And, maybe most incredibly, it's the core of MRI machines that let us see inside the human body without a single cut. So really, if there's one thing to take away from all this, it's this. By controlling how electricity flows, we can create and control real physical motion. We can make things move precisely and powerfully. It's one of the most important energy transformations we've ever figured out. You know, realizing that electricity and magnetism were one and the same was a monumental leap for physics. It really makes you wonder, doesn't it? What other forces out there? You know, things like gravity or the forces inside an atom. What if they're also just different sides of some deeper, unified theory we just haven't found yet? What's the next big connection that's just waiting for us to discover it?